right, hi everybody. Welcome to lecture 5. Today we're going to start thinking about stress-strain relations. If you have taken multiple graduate classes, this may be a little bit more of a review for you. But next week we'll get into some new materials. And if this is one of the first graduate classes you've ever taken, then hopefully you'll be able to connect a lot of things together that you've learned in the past with Hooke's Law. And then moving forward, we'll talk about plastic strain as well. All right. So when we talk about stress and strain, right, this all goes back to experiments that were done, right? So if we have a complex part, we have to be able to apply some theories to what's happening at every location on that part. But we derive those theories from a tensile specimen and tensile testing. So I'm just going to put some nomenclature down for us. So this is kind of a common shape for a tensile test specimen. It's often called a dog bone. It is symmetric, even though I've drawn it a little bit crazy. And it's got two shoulders on the ends, and those are the parts we don't care about. Those are the parts we put into a fixture. And then when the fixture is put on, then some load is applied to the ends, usually in a load frame. And we'll start out, let's say this has a circular cross section. So just kind of draw that in here. Right. And that circular cross section will have some diameter, right? We know what it is exactly. We've measured it before the experiment begins. And then what we do is we want to know what's happening in this middle section. So we determine that there are 2 points we're going to keep track of. And those 2 points, if the specimen is not yet deformed, are called the gauge length. Okay, it's between those 2 points. And then as the specimen is pulled, the distance that initially was the gauge length is going to increase, right? And so we'll start to define a few terms off of this. The first one is the engineering stress. And then I think our textbook calls that S, so I'm going to try to follow the same nomenclature. So that's S, and that's going to be equal to whatever the load is divided by the initial area, A naught, where the cross-sectional area of the specimen before it's deformed is called A naught. And so you can see that if we load up to some value, P, that will be a known value, and A naught does not change. So we're always dividing by the same area. Okay? And that's called the engineering stress. Okay, so we base that off of some initial condition that does not change. We can also define the engineering strain then, and that will be the change in strain, right, based against some initial condition that will not be changing. So if the gauge length, if we call that L naught, right, some sort of initial length, then the engineering strain, I'm just going to call that epsilon for now. We'll call it like epsilon engineering, is the final length of that gauge distance minus the initial gauge length divided by the initial gauge length. So that's our definition of engineering strain. Right? These should be very common definitions for you. And if we put this in a load frame and we extend it, then there's going to be a region where the specimen does not look any different, right? So if A naught is a circle, A naught remains a circle, and the specimen, if we were to, let's say, think about it in terms of its, let's say its engineering strain. I'm going to go to the next slide so I can draw this. So if we make a plot now of engineering strain versus engineering stress for some material, we would have an elastic region here. So I'm just going to draw it as a straight line, as straight as I can. And in that case, the gauge of the material, I'm just going to draw our little dog bone in a small distance here, in a schematic. It looks the same through the gauge distance. It's kind of a uniform diameter throughout. And then as the engineering strain continues, right, we might hit some kind of a yield threshold, right? It's going to keep going up like that. And it really doesn't change its shape too much here. So it's still in the elastic range. It's kind of going to look like that, and maybe in this initial ductile region. But as we start to really get into ductility and we go past the ultimate tensile strength or the ultimate strength, then the specimen itself will start to change shape. Right, so we still have our fixtures on the ends like this. But then we're going to start to get some sort of necking in the middle, right? And I drew it kind of crazy, but it starts to get a real thin section because we can't really change the volume of this thing too much. So eventually it's going to break. And then as it comes down to maybe a fracture or a complete yield point there, the necking will continue until the section is so thin that it can no longer sustain the load that's on it, and the specimen will fracture. So this is just kind of a qualitative chart of what happens during plasticity. And we're going to talk today about the elastic region. So I'll sort of mark that here. So we're going to talk today about the elastic region, stress and strain, and this initial plastic region here. Okay, so we're not going to be going into predicting anything when there's necking involved, when there's this severe plastic strain and there's dimensional change of cross sections. And that because that's exceedingly hard to predict, and when that's happening, there's usually some kind of collapse going on of a structure. So it's not like we would want to have a little bit of plastic deformation for work hardening or something like that. Which is what we will look at today, but rather that goes into this extreme condition. So we're really not going to work out here in that region. Okay. So corresponding to the engineering stress and strain, but with slightly different definitions, is the true stress and strain. So I'm going to go to the next slide here and redraw that same plot. So we'll have strain on this x-axis, stress on the y-axis. Okay, easy. And then we'll have our same plot as we did for the engineering values. So we have a linear region at the beginning, and then we might have some sort of a yield event. We'll go up, and then we'll go down, and we'll break. Okay, so this is the engineering curve that we get. If we always use that A naught and L naught and compare everything to that. We can also define something different called the true stress. So the true stress I'm not going to call S, I'm going to call it sigma, right? Because that's what we've been using when we've calculated our theoretical stress states. And so the true stress is the load, whatever it is, divided by the instantaneous area, cross-sectional area. Instantaneous area. So that's P divided by A, and I'm going to call it AI instead of A naught. Okay. And corresponding with that, we can get the true strain, right, which is defined as the natural log of the final length over the initial length. So we would have natural log of LF divided by L naught. That's the gauge length. And so these are our true values. And so if we plot those, the strain is not going to change that much. Strain changes a little bit, but strain is usually very small, right? So we're going to have the exact same elastic region. So I'm going to draw kind of right on top of that initial line in blue. That doesn't change. When we get into the second region, though, that's where the curves start to deviate a little bit. So we have some yield, and then this curve, whoops, that vertical line should not be there. That's kind of an error. It goes up like this, and then continues to go up until we get failure, something like here. And actually, that failure is going to occur out a little farther along the x-axis than the other one. So this is our true stress strain curve, because as we continue to pull on this specimen, the real area gets smaller and smaller, so it does not stay the same. So that's the big change here, is the stress starts to really deviate. So we are going to define, as I did before, this elastic regime. And then we'll have a second regime that we will study, which is going to be called a uniform plastic regime, okay? Where the ultimate, it goes basically up to that ultimate tensile strength, which is defined on the engineering stress strain curve. So if I draw a dashed line down from there, and then one that stops at the top of the elastic region, where that line starts to become nonlinear, this is going to be the uniform plastic region. Let me make sure I got everything here. And then we can also define the true, so we would have, if on the engineering curve, we could define some values here as well. Like if we came down from here, this would be the strain at break. And if we did the same for the true curve, right, we'd have a true strain to failure, be a little bit higher. And then we could have a true stress to failure up here. So you can kind of define some things, you can put a little tilde on top and call that the true stress to failure. Right? So when we go in the future and we start talking about what defines this uniform plastic region, we are going to follow the engineering stress strain curve, because that's what is pretty standard for all of these tensile tests. But we need to know what the true stress and strain are for some of our background theory. So now let's talk about how the engineering stress and strain relate to the true stress and strain. Okay, so the first thing that we can say is that the area in a true, sort of the true area, instantaneous area, times the instantaneous gauge length is equal to the initial area times the initial gauge length. Okay? Or we could call that AF and LF. Okay? And we're going to say that that is a constant. If we talk about Hooke's law and the volume changes that can occur, they're usually taken to be negligible when you compare it with stretching or bending. Okay? So what this means is an area times a length is equal to an area times a length, so that means volume is conserved. Okay? And so this is just so that we can get some equivalence between our states here. So we can say that the instantaneous area is equal to the initial area times initial length divided by some instantaneous length. And so we'll go back to our definition of true stress, which was P divided by AI. We'll plug that in, and we get P divided by A naught times a ratio Li to L naught. And then we would recognize that our definition of engineering stress is now inside of this definition of true stress and strain. So we'll say that the true stress is the engineering stress, S, times our final length divided by our initial length or any instantaneous length that we have. Yeah. We can also write this a different way if we want to. We can say that the real stress is equal to the engineering stress times 1 plus the engineering strain. If we just kind of work with those fractions a little bit. Okay. And then if we follow this along, we can say that the true strain is equal to the natural log of 1 plus the engineering strain, kind of through the same type of manipulations. So this is just some basic background on stress and strain and where it comes from and sort of some definitions. So when we get into a yield situation, we are going to have some strain hardening, okay? So let's draw this plot one more time. And so we're going to have now the engineering stress and the engineering strain, S. And let's say that we load a specimen up through its elastic range, and then we want to work harden it a little bit. We've heard about strain hardening, work hardening, so we're going to load it up a little bit past the yield point. All right, so we'll load it up to here, okay? So I've just drawn like a curve there. And so we can come here and we can label like the yield stress, right? So we know we've gone a little bit past that. And because I've curved it out, if I've stretched it out and now I release the load, it's going to come back a little bit, right? Because at the point where we stretch it to, we have both elastic and plastic deformation happening. So if I release it all the way back to 0 stress, it's going to come back down like this. All the way back to 0 stress, but there's an offset in the strain axis, right? Another way that you can describe a plot like this, where it doesn't follow itself, is that there's hysteresis, right? That's the fancy name for the plot doesn't lie on top of itself. There's a change in one condition. And the slope of that is pretty consistent, right? If the slope of our initial curve is defined as the elastic modulus, then the slope when we unload it, it's also going to be relatively the same, okay? Okay, good. And now let's reload it again and see what happens. So I changed colors, so we're going to reload it again, and it's going to basically follow the same, but then it's going to have a yield that goes like this, right? So we've effectively increased our yield stress. So I'm just going to draw it like, whoops, come on, pen. So on our second loading, now we've effectively increased the yield stress. Okay? And that is the definition of strain hardening or work hardening. And it always takes place in this stable plastic regime. And so when we unload it, we get back the elastic strain that we put in, but we don't get back the plastic strain. Okay? So I'm going to draw another piece on here along the x-axis. And so if I said we get back on the second loading, or when we release it, sorry, after the first loading, we don't get back our plastic strain. So this permanent strain or plastic strain is going to be the first little region right there at the beginning of the plot. So I've written kind of sigma p right there, or sorry, epsilon p. Right. And then when we load it a second time, right, then we actually are inducing a second round of elastic strain, right? So then I'll have epsilon little e for elastic. And then if I keep pulling on it, then it's going to yield again, right? And we can do this multiple times until we get too close to the ultimate strength, and then we start to lose this effect. Okay. And this happens based on what we talked about in the very first lecture, where if we keep pulling on a material past the elastic point, then the crystalline lattices move, dislocations are introduced, and as dislocations build up, they resist additional slips. So that's where this comes from. Okay, so how can we describe, let's say, this increase in our yield stress with the strain that's been induced? I'll draw an arrow right there. Okay, so what we can do is try to fit this to some sort of a curve that describes it. Okay? And so we measure this in a real sense. We measure engineering stress and engineering strain. If we transform it to true stress and strain, I'm going to draw that plot next to it right here, and we transform it from maybe a linear scale, something like that, to a log scale. I'm going to kind of draw some real units here, just as an example. So let's say on a true stress scale, that would be in kpsi, so thousands of psi. We'll have 100 here at the top. We'll have 10 in the middle, which I've left no place to label it. All right, 10 right there, and then 1 here on the bottom. So if we draw things on a log scale, then every linear, or every tick mark that looks linear to us is actually a factor of 10 going up. We can do the same thing on the y-axis. So true strain, and this is going to be in inch per inch. So this is not percent, but you could transform it into a percent. It's just length per length, so it's unitless. And so we'll start out, and we'll have a very small length here, like 1 times 10 to the minus 4. So I'm just going to write 10 to the minus 4. And then as we go up, we'll go up by factors of 10, so that gets real easy. So 10 to the minus 3, 10 to the minus 2, 10 to the minus 1, 10 to the 0, which is 1. Sorry, I didn't leave myself room to label it there. Okay. So now we can draw sort of an example curve on here for some sort of a metal. And so there'll be an elastic region that is linear on a linear plot, so it's also linear on a log-log plot. And then this line is going to change its slope, because as we get into that, past the yield point, right, the curve starts to have a curvy shape and a downward slope, right? So that means it's going to have a slope here like this that's less than 1. And it's going to have a power law relationship if it looks linear on a log-log scale. So let's see how that works out here. So we can write our expression that we had from the other chart, which was the strain, the total strain on, let's say, a second loading after it's work hardened, is going to be equal to the elastic strain plus the plastic strain. Right? So those two regions on the bottom of the first plot. And then if we think back to hang on, let me think about this. Relationship that we had, well, let me just write this down for now, but we'll talk about Hooke's law next. So we'll have a relationship where at least in the elastic region, let me draw an arrow there, where the true stress is equal to the elastic modulus times the true strain. And so if this is on a log-log scale, let's take the log of this and see how that matches up. So we'll take the log of the true stress, and then when we take the log of a product, it becomes the log of one plus the log of another. So we'll have the log of the elastic modulus plus the log of the strain. And then if we fit the top region that has the strain hardening, we'll come out with a different exponent that's not a 1-to-1. So I've run out of space here. So I'm just going to write this on the bottom, and we're not going to talk a lot about specifically where it comes from, but based on this kind of a plot, you can see that the engineering strain is going to be related to some kind of a coefficient, K, times a change in distance, let's call it delta, to some power n, where n is the strength hardening coefficient. All right. So sorry for the back and forth here, but I just wanted to show you on where the exponent comes from, because it's a logarithmic relationship. So we'll come back to this expression here, and we'll use it a little bit later on now that we know about it, when we get into multiple loadings and strength hardening. Okay. So that's just a little bit about stress-strain curves. Okay. So we're going to now talk about Hooke's law, okay? And we're going to go back to our cube where we had the stresses on it, and then we're going to apply what we know about stresses and strains now to get relationships between stress and strain, and we'll derive it systematically so that we can then extend that into the plastic region. Okay. So we're going to change what we know from a tensile test, or we're going to convert or apply. We're going to change a 1D situation to a 3D situation. We're going to go from 1D tensile test to 3D stress and strain. So let's go back and talk about the cube that we had. I'm just going to draw it like this, where we have the y-axis here, x-axis here, z-axis vertical. Excuse me. And in this case, we're just going to apply a tensile test in one direction and see what happens then. So all we're going to do is have sigma y here, nothing else. So this is effectively a small, infinitesimally small element in our tensile test. Okay? And so in our tensile test, if we're in the elastic regime, we can say that if we load it and unload it, it goes exactly back to where it was, and it acts like a spring. It acts like a linear spring. So that's our understanding that we're starting with. Right. So if this thing acts like a linear spring, we can write down the relationship between the force and the displacement for a linear spring. And I'm going to use the nomenclature that the book uses. Okay. So we had a dimension across our cube here of dy. And then we also have, I'll just draw these, dx is here, and dz is that vertical dimension. Okay. So this should be like very straightforward to everybody. So if we have a force in y and we want to convert it to a stress, because that's what we're working with here, we can say stress in y divided by dx dz. That's the face on which it acts. So that's equal to, whoops, sorry, that should be an f. Come on now. F y divided by that is equal to sigma y, which is now, if we do the right side of our equation, divide it by the same values, dx, dz, come up with something like that. Okay, so now we have a relationship between sigma y and some other terms that involve some sort of a spring constant on the right side. Okay, we got to keep going so that we get to some value that describes the compliance of the whole cube and not just a linear spring. So now let's isolate this term, this delta dy, which is the length that the cube will have to stretch. So it's dy plus delta dy. So that's the stretch distance of our linear spring model that we're kind of starting with. So we'll put that on the left side. So delta dy is equal to sigma y times dx dz divided by k. And I'm going to put a dy on both top and bottom here on the right side, and so that we can get a full volume term on that right side. So dx, dy, dz. All right, so if we think about that, that's the volume of that cube. Okay, so far so good. But how now do we get to a volume, right, where something has like an elastic modulus in it? So what we now do is define the elastic modulus as something related to our spring stiffness. So it's going to be the spring stiffness times dy squared divided by volume. Okay. And the units work out on this. If K is a spring constant, which is kind of newtons per meter, then we multiply by meters squared. Then we get Newton times meters divided by volume, newtons per meter squared. That's a pressure, which is our elastic modulus unit. So now let's substitute that into our initial equation, and we get delta dy is equal to sigma y times dy divided by E. Okay, so that's where that kind of comes from. And so this is a relationship between the distance we had to stretch and the stress that was initially applied. So now we can put that in terms of our strain. So I'm going to say epsilon yy is equal to the change in dy divided by dy. That's our definition of engineering strain. Right. And then that will also be equal to the input sigma y divided by E. Okay. So we're getting there. And we can then think about what happens on this cube in the other dimensions. So we've only talked about one dimension, y. We haven't talked about what happens in x or z. But if we have generally conserved volume, then we can't change the distance along y without changing the distance along x and z and reducing them such that the volume is generally the same. And so we can write now that the strain in the x direction, because of a stress in the y direction, I'm going to call that epsilon x y. So the stress in the x direction because of a stress in y is going to be equal to minus a coefficient times our strain that we had along y. And that coefficient is the Poisson ratio. So that's a ratio between the strain we get in the direction we're pulling and the strain in the other direction. And so we can write that also as minus Poisson ratio times sigma y over E. Okay, so I'm just going to box that. I know this slide's getting pretty crazy. And then we can do the same thing for zy. Okay? And the letter that we're using for Poisson ratio is the Greek letter nu. It is not a V, but it's a wavy V, so it's a nu. Okay. So we can do this for all three directions. And then we're getting there to what Hooke's law is, but we're not quite there yet. Okay. So let's do a little bit more manipulation with these values. So let's make a table where we have the direction of strain. Right, so we're going to have then direction of strain. So it's going to be x. Let me go change this to darker. Okay, x, y, and z. So that's the direction of strain, and then the stress causing the strain along the top. Right, so then we have a sigma x, sigma y, and sigma z. We're just going to make a table here. So we just did epsilon y, right? And we said that was sigma y divided by E. There's no Poisson ratio because it's the strain in y due to a stress in the y direction. And then we also defined the strain in y from, hang on a second, let me define it. That's not what we defined, hang on. We defined the other, yes, okay. So then, no, that's what we defined. Yeah, so this is the strain in y because of a stress in x. This chart is messing me up. All right, let's do the ones across first. So strain in x because of a stress in y, right? So that's what we just defined. So it's minus nu times sigma y divided by E. And then the strain in z from the y is the same definition, minus nu sigma y divided by E. Okay, so we have 3 values there. And then what we can do is expand this correspondingly to the other values. So we'll start with just x and z. So we can have epsilon xx is equal to sigma x divided by E. And epsilon zz is equal to sigma z divided by E. Right. So that's pretty straightforward. And then we can do the other combinations. So if we have stress in x, but it causes a direction of strain in z, then we have sigma xz, so that's the bottom left, is minus nu times sigma z divided by, sigma x. No, now I know why I'm messed up, because I can't read these numbers. Okay. This is a really confusing table. Let's say this is sigma z. So we have x, y, and z. I think these axes should be flipped. One moment. Yeah. If we go by the definition we had before, where the first, let's just write it up here. So E epsilon xy is strain in this direction due to a stress in that direction. I'm going to fix this table. Yes. Okay. So rather than rewrite the equations in the middle, I'm going to change the axes. I apologize for this, but I want to get it right. So if we have sigma xx, xy, and xz, those all go in the x direction. So basically these are going to be flipped, these here. So this top part is going to be the direction. So it's going to be x, y, and z. That's why it is the first index. Okay, and then this y part of the chart, I apologize for this, is going to be the stress that causes that strain. So all of these are going to be a function of sigma x, those sigma y, and these sigma z. All right, now the chart will be correct. Okay. So we can fill this in. So let's see, epsilon yz minus nu sigma z over E. So now, now it follows the convention correctly. Okay, sigma y minus nu, sigma x divided by E, and epsilon y, z x minus nu sigma z over, sigma x divided by E. Okay, goodness sakes. All right, I apologize for the messiness on this. I would recommend looking in the textbook and making a table for yourself that is a little bit more clear. let me just see, XYZ, 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 XYZ. Okay. So let's look at this table now, even though it's a little bit messy, and think about all of the strains that go in the same direction. Okay. So let's say we went back to our strains along Y because of a stress along Y. So that's the center column here. All right, so I'm just going to circle it. Okay, circle it in some yellow here. So that's all the strains in the Y direction due to the stress in the Y direction. Some of them are because we're going in the same direction. We're literally pulling in that direction. But there are strains as well due to the contraction along the other dimensions of the cube, right? So let's think about all of the strains that are in one direction because of that stress that's applied. And so we can say that the strain in Y is equal to all of the components of strain in Y. So strain in Y due to X plus strain in Y due to Y plus strain in Y due to that contraction in Z. So at any location in that cube, right, then these will all sum up. So now we can convert this based on these expressions that we have, because we're not going to be measuring strain in all these directions. What we measure, or what we think about, is stress. So we're going to substitute in the expressions for stress into this equation. So I'm going to write substitute stress into here. Okay. And that is Hooke's law. So go to the next slide. So let's write that down. So strain epsilon x is going to be equal to 1 over the elastic modulus E. That's in all the terms. Times the quantity of sigma x minus nu, Poisson ratio, and it's minus nu times the stresses in the other direction. So it's minus nu times sigma y plus sigma z. And then we can say the same thing for y and z. So sigma y is equal to 1 over E sigma y minus nu times the stresses in the other directions. And strain in Z, the same thing. Okay. So that is a derivation of Hooke's law based on observations from tensile tests and applying that from a 1D tensile test into a 3D space. Okay. So now this applies for any situation. Okay, we're give me one moment. Okay, so we talked in the prior lecture about principal stresses. And so now we're going to also talk about principal strains that go along with that, right? So these expressions that I've written up here are in terms of x, y, and z, right? If we wanted to calculate the principal stresses, we could do that. And they actually relate similarly to the principal strains, okay? If we said that for any given situation, this XYZ coordinate system is our principal coordinate system. Let's just say that we solved it and XYZ is equal to 1, 2, and 3 in this case. Then we can rewrite these equations, right? We can say that E1 is equal to 1 over the elastic modulus times the first principal shear stress minus nu times the second principal shear stress plus the third, right? So we talked about that with Moore's circle, where sigma 1 is always greater than sigma 2 is always greater than sigma 3. And so in this way, we can get not only the principal stresses, right, from solving our matrices and stuff, but now we can get the principal strain. And then we can compare the principal strain to, let's say, a strain to failure, or a strain, the strain that exists when the material yields, right? And we can determine, did this material yield or not, right? Based on a complex state of stress rather than just a 1D tensile test. And we can do the same thing for the second principal strain and the third principal strain. It's not as helpful, but we can say that. So I think I'm going to stop that lecture here, and then we're also going to make some notes about shear strains in the next lecture, and then we're going to expand this to the plastic regime, okay? So for a lot of you, I know this was a review, but now it's fresh in your mind where these things come from. So we'll stop there and we'll pick back up in lecture 6.